So now that we've got our vocabulary, which I want to talk about Ohm's Law. I wrote it in blue, so it's not all that clear. Ohm's Law. Now, Ohm's Law is one of those laws like Newton's universal gravitational law. It's not a law. Ohm's Law only applies for devices that are ohmic. Okay, which is a device that obeys Ohm's Law. So it's kind of a bit of circular logic. Another way of looking at it is, let's say I come up with a law. My name is Derek, so this is Derek's law. Derek's law says that all vegetables are going to be red. Okay? Under the caveat that it only applies to Derek's law of vegetables, which so happen to be red. Now, it's obvious that not all vegetables are red, but for those vegetables that are red, they follow Derek's law. Okay? That makes sense? It's not really a law, but it is a law. It's a law that only applies to particular types of devices. And there are everyday examples of devices that are not ohmic. Excuse me, a light bulb is a non-ohmic device. It begins to behave ohmically, but it's not an ohmic device. Okay, so Ohm's law says voltage is equal to current times resistance. That is Ohm's law. Okay? Now the problem with the way in which this is presented to you, it looks like that potential is the product of current times resistance. That potential somehow is created when current and resistance is applied. The truth of the matter is that current is created when you have a circuit that has resistance and voltage. Okay? So current is the result of an ohmic device. This voltage, this resistance produces a current. Okay? So a better way of expressing this would be to say that V over R is equal to I. Okay? That'd be a better way of expressing it, but this is Ohm's law, V equals IR. That's the way you're going to see it. But understand that what we're trying to say is that a current is produced when a circuit has a potential difference of voltage and a resistance. Now, I'm going to draw a really quick simple circuit. So a really quick simple circuit has a battery, okay, cool. It has a resistor, and that resistor connects both ends of that battery, okay? That's a simple circuit. Now, you may see a circuit that looks really familiar to this. You may end up looking something like this. That's the exact same thing. Okay? This is a standard notation I've always used. This is a symbol for resistance. This is a symbol I've seen in other books. So there's no kind of consensus on the symbol for resistance. So either one of those you may encounter. Okay, so here's my battery. Here's my potential difference, my voltage, right here too. And then here are my resistance. That's a simple circuit. So what that ends up doing is that this voltage, this potential difference here, motivates a charge to move. Now what charges move more often than others? Well, electrons. Protons are bound. They're in the nucleus. It's the heaviest part of an atom. It takes a lot to motivate that nucleus to move. And more than likely, those nucleuses are bound to other nuclei, making a molecule, you know? So they're not really all that motivated to move. Where electrons, especially on things that we use for electrical current, like copper, like gold, those electrons tend to be liberated. They tend to be free. They tend to move quite easily. So I apply that potential difference, and I start moving electrons. So electrons move through my circuit, and they come back on the other end. Now, why do they do that? Why do electrons move? It's the same reason that a rock rolls down a hill. It goes from that high energy state. Let me get into the screen a little better. That high energy state at the top of that mountain. the high energy state, and it wants to go down to the low energy state at the bottom of the mountain. Okay? So the electron starts off at a high energy state and sees a low energy state at the bottom of that hill. So what does it do? It falls down that hill and goes to the low energy state. Now, the thing about electrons is that they're negative charges. So to say high energy here is also to say low potential. Okay? To say low energy here at the bottom here, this side, is to say that it has high potential. Okay? Because you're taking that high numerical value, that 12, that 15, that 100, and you're multiplying it by a -1, whatever, making it a very, very low number. Okay? So that's why it goes from high energy, low potential at the top, to low energy, high potential at the bottom. Because it's an electron. Electrons like to break the rules. Now, the other thing that we got to realize is that when we talked about current, current is going to be coulombs per second. It's not talking about negative coulombs per second. It's talking about coulombs per second. So even though my electrons are moving, and we know that they're what's moving and not the proton, they're moving in this direction, my current is moving in the opposite direction. Okay, it's moving in the opposite direction of those electrons. That's because current is the motion of positive charges, positive charge per time. And so that's the direction in which my current is traveling, in the opposite direction of my electron. Now, if you want to blame somebody about that, blame Ben Franklin. He's the one that decided that electrons are negative charged. Okay? Cool? Got it? That is Ohm's law. Now let's talk about what actually is going on. So this right here, the analogy that's often used to talk about Ohm's law and talk about simple circuits is water. Think of your potential as being a water pump. If I've got a strong water pump, I have a lot of pressure. Pressure that wants to move the water through the series of pipes. Okay? The resistance is the type of pipe. Now, that can mean several things. You may have stuff in the pipe. You may have gravel in the pipe. You may have filters in the pipe. It may be a thin pipe. It may be a wide pipe. All these things play into effect in resistance. And then the amount of current is the amount of water that flows from that water pump all the way back around. Okay? So the amount of water per second that's flowing out of that water pump, my voltage, all the way around. Okay? So you can see why resistance is this property that we use to talk about filters and gravels and diameters and, is it small, is it big, how that can affect the amount of water that's being left by my water pump and is returned back to the system. Okay? Cool? That's a very simple circuit. It's a very simple circuit, and that's Ohm's law.